So let us turn now to integrate both aspects of chemical reactions. First of all, the diffusion process, whereby reactants come together to meet one another in solution, and then the chemical reaction that follows at a rate controlled by the free energy difference between reactants and products. I'm going to illustrate this with the so-called Michaelis-Menten model of enzyme kinetics. An enzyme is a protein that catalyzes chemical reactions. So, for example, it might catalyze the breaking of the backbone of another protein. The substance on which the enzyme acts is called its substrate. So if we have some concentration here of enzyme and substrate, it will go at a rate depending on the concentration of enzyme and substrate and the diffusion constants in solution, K on, to form a bound complex ES. Depending on the binding energy of this complex, there will be some Boltzmann factor for the reverse process, which is the unproductive dissociation of the complex at a rate K off. And there will be a competing process given by a rate constant K2 in which ES reacts to form the free enzyme and the product, in this case the cut proteins. So we can then write down our rate equation for the time rate of change of the enzyme substrate complex from the equation above, and then the rate at which the complex is lost. So we're going to make several assumptions to simplify the kinetics. Remember, the concentration of enzyme and substrate are changing with time. And our assumptions are going to be that the rate limiting step is dominated by K2 for the formation of product. So with that then, we can say that the time rate of change of product is given by K2 times the concentration of the bound complex. The second thing we're going to say is that if the concentration of enzyme and substrate is very high, then this overall reaction rate here is going to be 0 because the concentration of the bound complex, enzyme and substrate, is not changing significantly with time. And the third thing we are going to assume is that the concentration, total concentration of enzyme remains constant at its initial value if we add together both the free enzyme and the bound enzyme concentration. So with these three equations here, we can substitute, first of all, this relationship into this equation, and then secondly, we will substitute into this first equation here. So when we do that, we end up with the following expression, substituting into equation 2, E0, and then what we're going to do is divide everything by the K on term that occurs here, and we're going to call this quantity a new quantity, the Michaelis-Menten constant Km. So Km is K off plus K2 divided by K on. If we do this and then use this equation to obtain ES and substitute it into equation 1, so that the rate of product formation is K2 ES in this limit of high substrate and enzyme concentration, then we will arrive at the following expression for the rate at which the reaction proceeds. This is the Michaelis-Menten expression for the rate of this reaction. Let's take a look at what it means and how to interpret it. So, to remind you then, we have that the rate of product formation is given by this expression. This is the maximum possible rate of product formation. This occurs at a state where all of the enzyme is bound, and therefore the reaction proceeds at a rate given by the highest possible concentration of enzyme substrate complex. However, as one decreases substrate concentration, the binding of the enzyme to the substrate decreases and the reaction rate decreases. So calling this the reaction rate and plotting this out versus the concentration of substrate, at very high substrate concentration, then the reaction rate is just the maximum possible reaction rate. As the substrate concentration goes to 0, the reaction rate falls to 0, and when the substrate concentration is exactly equal to Km, then the reaction rate is half of the maximum. So the Michaelis-Menten equation gives a prediction like this for the rate of reaction versus substrate concentration. And indeed that is observed in many enzyme-substrate reactions. Let us turn to consider a little more the situation in which the reaction rate is controlled now by the binding event in the first step, as opposed to the reaction event in the second step. In this case, remember that Km, which is K off plus K2 over K on, let the reaction rate go to 0, so now we are considering purely the rate of the process as determined by the collisions in solution. In that case, we call Km a new constant, Kd, the dissociation constant. And this is given then by K off over K on. This, of course, corresponds to the first step, and the kinetics are controlled purely by the binding energy of the complex. So there will be an on rate given by this transition state and an off rate given by this delta G difference between the bound and unbound complexes. Now, the on rate is dominated by the rate at which particles in solution simply bump into one another, and this depends really just on the concentration of particles and the diffusion constant. So there is a calculation in the back of the book by Howard, referred to at the end of chapter 3, which shows that the maximum possible rate at which this can occur in room temperature for typical diffusion constants is 10 to the 9 per mole per second. So at a concentration of 1 molar of reactants, then, the time between for reactant and product to bind is 1 nanosecond, so they meet each other at a frequency of 1 gigahertz. In practice, for biological complexes, they have both to collide with one another and do so in the right orientation, and a more typical value of K-on for biological complexes is about 10 to the 6 per mole per second. The off rate, on the other hand, is given purely by this delta G here for the bound complex, and is characteristic of the strength of binding. So overall, the dissociation constant then is a good measure of the strength of an interaction. Things that bind very strongly may have dissociation constants in the nanomolar or sub-nanomolar range, whereas things that bind rather weakly may have dissociation constants on the order of micromoles.